This video is the supplementary material to our paper. The aerial manipulator considered in this paper consists of a quadcopter base and a delta arm. The overall control system of the aerial manipulator is decomposed into three components. The first component is the cooperative planner. A novel cooperative planner with two modes is proposed to coordinate the motions of the quadcopter and the manipulator. The physical constraints of the aerial manipulator are transformed to reduce the computation cost of the planner. To adapt for different manipulation tasks, two control modes, PP and EP, are proposed. The second component is the flight controller for the quadcopter base. We propose a novel flight controller for aerial manipulator that consists of extended state observers, ESOs, for dynamic coupling estimation and ESO-based flight controllers. The third component, the delta arm controller. The delta arm controller is constituted by three actuator controllers. The ESO-based flight controller runs on a Pixhawk 4 autopilot. The cooperative planner and the inverse kinematics of the delta arm run on an onboard Intel NUC i7 computer with ROS. The experiments are conducted in a Vicon system, which can provide accurate position. The purpose of this experiment is to verify the effectiveness of the ESO and the flight controller. A PX4 controller is selected as a baseline for comparison. A payload of 1.2 kg is mounted at the end of the delta arm. The control objective is to maintain the position of the quadcopter base unchanged while the payload swings fast. Compared to the PX4 controller, our proposed controller can reduce the mean and maximum position errors by 78% and 80%, respectively. The purpose of this experiment is to validate the PP mode of the proposed cooperative planner together with the flight controller. The control objective of this experiment is to stabilize the end-effector to a fixed position while the quadcopter is flying along a circle with radius of 6 cm. This scenario considered in this experiment is important because practical tasks may require to assign separate trajectories for the quadcopter base and the end-effector. For example, the end-effector must track a desired trajectory to complete a manipulating task, whereas the quadcopter base must move to avoid obstacles or observe the manipulating target from different angles using onboard cameras. The mean position error of the end-effector is 0.011 meter. The purpose of this experiment is to validate the EP mode of the proposed cooperative planner together with the flight controller. The control objective in the third experiment is that the end-effector can accurately track a desired complex trajectory. Different from the second example, this example does not require to specify the desired trajectory of the quadcopter base. The mean tracking error of the end-effector is as low as 0.01 meter. In the final example, a rope is tied at the end-effector. The control objective is that the end-effector must pass through 4 hangars precisely and complete an aerial weaving task. As shown in the video, the task is successfully completed by the proposed method. In particular, the mean tracking error of the end-effector is 0.02 meter, which is greater compared to the third example where the mean tracking error is 0.01 meter. This is reasonable due to the drag force of the rope. Since force control is not specifically considered in our algorithms, the present performance verifies the ability of the proposed algorithm to counter external forces applied to the end-effector.